In this video, we're going to look at a special kind of discrete probability known as the binomial distribution. We're going to look at what the binomial distribution even is, and then how we can use it to solve discrete probability questions faster than we otherwise would be able to. For those who don't know me, my name is Chris Inazzoni. I used to work as an engineer for a defense company, and I left that to start a career in tutoring. I make these videos for VCE students so that they can do the best they can in math methods. With that out of the way, let's get into it. The binomial distribution is a special kind of discrete probability that meets the following criteria. First is that there's only two outcomes. Usually this is framed as either a success or a failure. The second is that repeated trials of the experiment are independent. And then lastly is that the probabilities of each given trial cannot change. The typical example of a binomial experiment is the coin toss. You have either a head or a tail, those are your two outcomes, and the probabilities don't change from trial to trial. It doesn't matter if you're on your first toss or on your 50th toss, the probabilities of getting a head or a tail is still just going to be 50-50. Binomial probabilities are solved using the Bernoulli sequence. This is an equation which tells you the probability of getting any number of successes, where n is the number of times that you repeat the experiment, sometimes referred to as the number of trials. P is the probability of getting a success. That's going to depend from question to question. And x is just the number of successes that you're after. So let's apply that to this example. We're tossing the coin a total of 5 times, so n equals 5. We're looking for 4 heads, so x equals 4. And the probability of a success is defined as tossing a head, and so that's going to be a probability p equals a half. All we're going to do is sub into the equation and simplify. If you need a refresher on how to simplify the factorials, then check out my video on counting methods. I've left a link in the description for you. If you want to solve this on a CAS, the syntax will differ depending on which CAS you have. On the TI Inspire, all you have to do is go to Menu, Probability, Distributions, and then Binomial PDF. It will always give you a decimal answer, so if you want to convert that to a fraction, just be sure to go to Menu, Number, and then Approximate to Fraction. On the Casio, it's found under Interactive, Distributions, Discrete, and then Binomial PDF. And again, if you want to convert to a fraction, on the Casio it's ever so slightly different. You're just going to click the Convert button at the top left corner. Sometimes you want to solve the probabilities over an interval of x values rather than a specific value. In these circumstances, or at least in a tech-free environment, you would treat it like discrete, where all you're going to do is add up all the probabilities in that interval. So if we're looking at tossing 1 or fewer heads, then all we're going to do is add the probabilities x equals 0 and x equals 1. If you're solving this on the CAS, again there's going to be 2 different scenarios. On the TI Inspire, you're looking for Menu, Probability, Distributions, Binomial CDF, and if you're looking on the Casio, then it's going to be under Interactive, Distributions, Discrete, Binomial CDF. Both are going to give you a similar looking setup window where you can plug in the interval, the n value, and the p. In tech-free scenarios, using complement probabilities can greatly reduce the amount of effort that it takes to solve certain kinds of probability questions. For example, if I want to find the probability of getting 1 or more heads, then I might add the probabilities x equals 1 to x equals 2 to 3 to 4 to 5, and then add them all together, get my final probability, but that will take a really long time to write out by hand. There's a better way. Instead, we're going to calculate the complement to this. The complement to x greater than or equal to 1 is x equals 0. And solving 1 minus the probability of x equals 0 is much simpler because you only have to solve one Bernoulli sequence. Some questions, like this one, absolutely require the use of complement probabilities. Specifically, these are the types of questions where n, the number of trials, is unknown. First, we're told the probability of a win is 0.25, so that's going to be our p-value. The next thing we're told is that we're looking for 2 or more wins. So again, we can write that expression down as well. We're also told that that probability should be greater than 0.9. So we're just going to apply that inequality to that expression. All you want to do here is expand out that probability using the Bernoulli sequence. But here's where the issue comes in. We don't know where to stop because we don't know the number n. We can't just do x equals 2 plus x equals 3, 4, 5, 6. We don't know when to actually stop that sequence. This is the advantage of using complement probabilities. If we're instead using complement probabilities, we do have an absolute lower bound of 0. So if you want to find the complement, it's just going to be 1 minus x equals 0 and x equals 1. Don't forget to use the brackets here. It's very easy to forget you're subtracting everything, not just the leading term. Now, we're just going to expand out that probability using the Bernoulli sequence, and that's going to give us an expression for n. It's worth noting that you should probably do these terms individually. Solve the probability of x equals 0 first, then the x equals 1, add them together, and that gives you your full expression. Makes things just a little bit neater. This is where the CAS comes in. For whatever reason, the CAS really just doesn't like inequalities for this type of question. So all we're going to do to get around that is just use an equal sign. That's going to give you two solutions. The negative result is invalid. We can't have a negative number of trials. So the 14.04 is where we're going to start. All we're going to do is figure out how to round it. But do you round up or down? Well, this just comes back to what probability we're after. We want the total probability to be greater than 0.9. So if we round one way versus another, we want to figure out which one of those gets us above 0.9. So we're just going to try both of them. If you define your expression as a function, all you have to do is sub in 14 versus 15 and see which ones get you above 0.9. And when you do that, you find out that n equals 15 is the only solution for this. Conditional probabilities always start out the same way. We start by writing out the conditional probability equation. Once we have that, we're going to focus on simplifying the numerator. There's two inequalities in the numerator, and we want to find the intersection between the two of them. And you can do this visually using a number line. Having done that, we can see that the numerator is just the probability that x is between 2 and 4. This is a range of values, hence the binomial CDF will be used. We can say the exact same thing for the denominator as well. From there, we just perform the division and then simplify the result to 3 decimal places, since that's what the question asked. If you found this video helpful and would like to see more, I actually have all sorts of additional resources available for free on my website. Just click the link in the description and you can access them here. And if you'd like my personal help, then consider signing up for the tutoring program. I offer the first 2 weeks free of charge, so you can get a feel for whether or not this will be a good fit for you. Otherwise, I'll see you in the next video.